from our department is going to introduce today's speaker.
Today we are happy to welcome Wayne Deeter from Oregon, just south of Eugene, Oregon, who is a man of so many parts that I wouldn't even attempt to list them, let alone go into detail about them. He's going to talk about a topic in dealing with convex polyhedra that began to be studied in the 18th century and has in the last 2 decades steadily received more and more attention from applied mathematicians, from biologists, and from chemists than ever before because of its perceived connections to some topics that in those fields that Wayne will be referring to. Now, it happens, parenthetically, that in 1974, the popular mathematics writer and genuine research mathematician Ian Stewart from Warwick University in England spent the summer at SIU, and I had the good luck to meet him in the student center at lunch one day, and occasionally throughout that summer while he was here, I got to know him.
When was this?
Pardon me?
When was this?
1974. It's possible that I'm off by a year and it was 75, but I don't think so. I think it was my first summer at SIU. I came all of 73. And in this book, which I bought some years ago, you see how yellow the pages are, there is a very witty, he's a Martin Gardner update. Unlike Martin Gardner, Ian Stewart is a genuine research mathematician. As you probably know, should know if you don't, Martin Gardner never studied mathematics, but he soaked into his brain mathematical insights by talking to such people as John Horton Conway and others, and then in prose that has never been improved on, he wrote popularizations of mathematical topics that pleased his readers for decades. In 28 years, he wrote a regular column called Mathematical Recreations in Scientific American magazine. Anyway, one of the aspects of today's topic, which is, if you want to go for the fancy name invented in the 18th century, the isoparametric problem for polyhedra. William will explain to you what that means. Basically, it has to do with, Wayne will explain it. I'll leave it to him. One of the topics is the topic of Goldberg Polyhedra. And I thought until this morning that sharing with Wayne the obsessive fascination with the music of Bach, I thought that Goldberg variations would be a good name for what Wayne has done, because he has introduced variations on the classical treatment of Goldberg polyhedra. But to my great discomfiture this morning on the internet, I discovered somebody beat me to it. There is somebody else calls his own treatment of the Goldberg polyhedra Goldberg variations. I had the great pleasure of knowing Michael Goldberg in the 60s. I used at least 3 or 4 times. It's time for me to quit, right?
Yes.
Okay. I'll wind it up. Anyway, this book called Game, Set, and Math is a witty book that includes a fascinating chapter that I'm showing you here about Goldberg polyhedra, which is one of the topics that Wayne has done pioneering investigations of. And I'll exceed myself a lot of time limit by another 30 seconds just to tell you that last April I first heard of Wayne when he sent me an email and told me about his work on polyhedra. And we have had a continuing correspondence between early April and now that led to his being invited to spend a week here as, what did Joe Deacon call it, artist in transit?
Yeah, that's right.
On the move, apparently.
Yeah, that's right.
Anyway, Joe Deacon, the head of the New Blankets Foundation, a probabilist and statistician, Joe Deacon, a man about town when it comes to public spirited enterprises. He's responsible for bringing me away in here for this week, and we're greatly indebted to him. Okay, I've exceeded my time limit by at least 90 seconds. Thank you.
Okay. The isoparametric problem for polyhedra is looking for a polyhedron of the given number of faces n that has the smallest area to volume ratio. Otherwise, to get rid of the scaling problem, it's generally measured surface area cubed over volume squared. And a fellow by the name of Lindelof proved that there are two conditions necessary for a polyhedron to be minimal in that sense. One is that the faces be tangent to a sphere, and the other is that that point of tangency be the centroid, the center of gravity of that face. Now, there's not a whole lot of polyhedra that have been proven to be the best. The first is the tetrahedron, the regular tetrahedron, and the triangular prism, the cube, of course, and then the great dodecahedron. Michael Goldberg started in about 1935. He published a paper, and he commented that prior people had considered as candidates prisms and bicapped, pyramidally bicapped prisms as candidates. But he noted that the limit of that is cylinders and cylinders bicapped by cones, which do not are much worse than a sphere as a limit. So he came up with the idea of a medial polyhedron. A medial polyhedron is a simple polyhedron that is, there are three faces joining at each vertex, and the faces are either n-gons or n+1 gons. So in the case of the tetrahedron through the cube, that's 3 or 4-sided faces. The cube through the dodecahedron, that's 4 or 5-sided faces. And above the dodecahedron, that's 5 and 6-sided faces. And he proposed that all solutions to the isoparametric problem would be medial polyhedra, except for 11 and 13, for which if you try to create an 11 or 13-sided medial polyhedron, you'll discover it's impossible. Another thing he did is right up here. In his paper, he gave a number of possible solutions for various n, and he skipped up from about 20 through 32. 32 is, he gave as a possible solution the truncated icosahedron, which is 32 sides, and so it's very symmetrical. It has icosahedral symmetry. And in a later paper, he expanded on that with what are now known as the Goldberg Polyhedra. Now, the Goldberg Polyhedra use an icosahedron as a generating polyhedron. All of the faces are laid out on a hexagonal grid, and you do R steps to the right, and then S steps at a 60 degree diagonal on this hexagonal lattice, and that's the base of a triangle for your icosahedron. And then you build an equilateral triangle on top of that. Now, because you have six-fold symmetry around each center of the hexagon, you can do that, and the third vertex will end up in the middle of another hexagon. And also, the edges will cut across the hexagon lines the same. So you can lay out icosahedron. For those who do not know, this is an icosahedron, 20 sides. It's one of the platonic solids. It's very regular. It's got icosahedral symmetry, so it's got 6 axes of 5-fold symmetry. It's got 10 axes of 3-fold symmetry, and it's got 15 axes of 2-fold symmetry. So, if we were...
Why don't you put your fingers on the opposite where it's about? Show with your fingers where those axes penetrate the figure.
Oh, you mean like that?
Yeah, right, in the face centers.
And then down through here, and then along the edges.
People aren't familiar with that, because you
Yeah.
detail that you may not be aware of.
So anyway, you cover the icosahedron with hexagonal lattice like that, and forget about the icosahedron now. So the lattice will be your edges and your vertices of the Goldberg polyhedron. Goldberg did not have a way of giving coordinates to all the vertices, though. He just specified the relationship of all the faces. But anyway, from this we end up with an infinite class of polyhedra that can be very round. So that's probably why he was looking at this. And have icosahedral symmetry. Now, this equation gives you the number of faces for a Goldberg polyhedron based on your R and your S. Now, S can be 0, and in that case, you'll have the base of your triangle cutting through those like that. Okay, I'll get back to the Goldberg polyhedra in a little bit. Next we get on to Allen's program. In about 85, Allen got interested in this problem and wrote a program to what's known as a Monte Carlo program that peppered a sphere with n points at random, using those as normal vectors, unit normal vectors. The perpendiculars to those become planes, and you figure out where those planes intersect, and that defines a polyhedron. Then, based on going back to the Lindenolf's conditions, you need to get the centroids of the faces coincident with the normal vectors. So if you roll the faces towards the centroids a little bit, and then go through the whole process again. Now, during that process, the polyhedron might change type. It might change to different shapes of the faces, but eventually it would converge in on a solution where it seemed to converge to have the normals be coincident with the centroids. And from that, he found, well, first, Goldberg had hypothesized that you might have a best that had no symmetry. And that's what Alan found, which is this one right here. At 25 sides, n equals 25, he found that there was a case with no symmetry. It almost has symmetry. I've forgotten where you said that the break point.
Pass around, if anybody's curious, they can find the four faces that spoil the symmetry.
Oh, okay.
The four faces are read in a book apparently about Steiner.
Yeah. And
Steiner street problem.
the next one he found was 33 here, which has a heptagon. So it is not a medial. So Goldberg was wrong with that conjecture. You want to pass this around?
But as Wayne knows well, Goldberg was a cautious man, he innovative, and he was a cautious man. He allowed for the possibility that his conjectures might be wrong. So, didn't he?
I don't remember what he said about
I'm
that.
not sure.
I think he was fairly tentative about it, and
I think he was.
in that, it's a conjecture. It's not. He didn't have a proof.
When
He
you
had
don't
an
ask people
intuition.
not to take the soccer ball.
Yeah, this is your 32 case, which, as I said, is a truncated icosahedron. Yeah, it's truncated icosahedron, except in its optimized form, the hexagons are not regular, unlike the Archimedean solid. So,
Any Brazilians in the audience, please don't kick this ball.
so 32 and 33 are very similar, except that 33 has an extra face and heptagon. So,
Do all three of those have this Lindelof property that the inscribed sphere is
Everything
Yeah.
is
touches
everything
at
is true
the
except those white
touches
bubbles.
at the centroid of each face?
that's correct. That in order to be the roundest, that they need to meet those two properties.
Within 1 part of 10 to the 12th.
Yeah. That's what the program, because it's a computer program.
Double precision fortune.
So where were we?
The stationary states, so-called.
So when I got into this a year ago, initially I was trying to do it by producing a catalog of all possible medial polyhedra, and then trying to get them
You
to
might
meet.
begin with a medial polyhedron.
Yeah, that's what I said earlier. A medial polyhedron has n and n+1 gons as faces, and it's a simple polyhedron, meaning three faces needed each vertex.
Simple means, that's the definition of a simple polyhedron.
Yes.
You were making catalog.
Yeah. Because I was going back to Goldberg's original article and assuming that his conjecture was correct, which it seems like a reasonable conjecture. And so assuming that it was correct, I was building catalogs of all these polyhedra, and then using similar algorithm to what Alan had that I developed independently. I was trying to get them into what Alan calls stabilized form, which are the two Lindelof conditions. The tangent to a sphere at the centroid, at face centroids. At that point, I ran into Alan's paper and re-implemented his program from his excellent write-up in his description of his program in his paper, and started cranking out. The reason I contacted him was because I discovered that his value for 37 was, I had a better solution than his 37.
That's no fair. His computer ran 1,000 times faster because 29 years had intervened since I did my work. And computers were now at least 1,000 times faster.
Yep.
I plead guilty.
And then I started running essentially his program that I had recreated, rewritten. And what I discovered, well, even Alan's supplement, he had talked about 42, he had, which is the second Goldberg polyhedron. And what he found for that was not a Goldberg polyhedron, and in fact, the Goldberg polyhedron is not the best in that case, which we'll get back to. I found several more cases which had no symmetry: 87, 93, 96, 99, and eventually I found another case that had a heptagon, which really surprised me: 140. Now, to get back to the Goldberg polyhedra, they're very round, of course, and you expect, every medial polyhedron 12 and above has exactly 12 pentagons. And you can work that out from the Euler characteristic. The Euler characteristic says that the number of faces on a polyhedron plus the number of vertices minus the number of edges is equal to 2. Now, based on that, you can work it out for a simple polyhedron and discover that when you only have n and n plus 1 gons, for 12 and above, you must have exactly 12 pentagons. So, but once you add a heptagon, you need to add another pentagon too to make it work out. But anyway, it seems reasonable that the pentagons should migrate to the vertices of an icosahedron to be maximally separated. And that's where they'll be for a Goldberg polyhedron, since it's constructed on a icosahedron. You'll notice that around each vertex of the icosahedron, you have exactly 300 degrees, and that's how the pentagons form. Is you lose one side of your hexagon out of the lattice at the icosahedral vertices. Now, so we found that some Goldberg polyhedra seem to be the best and others don't. One thing you notice that was in common with the ones that aren't the best is they always had a 0 for the S. So there seemed to be something about that made them less than optimal. So I took the basic program and ran it in what's known as fixed vertex set mode. You don't allow the type to change, and plugged in various Goldberg polyhedra, and was able to work up to 16,000 face Goldberg polyhedra. And eventually I also made use of that icosahedral symmetry. You only need to compute for every face, but it's even better than that. You only need to compute for a third of a face. Because of the symmetry, you can wrap it around itself to simulate the entire polyhedron, but only compute 1/60th of it. So with that, I was able to push up to 6 million faces and get areas for these Goldberg polyhedra. Now, one of the things is, with this equation right here, you'll find that there are certain n that you can get to with different r's and s's. So you have Goldberg pairs. And so that provides a way to probe this. For example, the lowest numbered one is 5, 3 and 7, 0. So 7, 0 will be 7 squared, 490, 492, whereas 5, 3 will be 25 plus 15 plus 9, which is 49, the same as 7 squared. And there's an infinite number of those. So I was looking at Goldberg pairs and comparing them, and found that going up to 6 million, you tend to have a lower area when you're closer to 1-to-1 for RNS. So that suggests that when you build these at approximately a 60-degree angle on the lattice, that you get a lower area than you do when you build it at a 0-degree angle. Now, another way I looked at probing this was to go to what I'm calling a generalized Goldberg polyhedron. Now, in Fowler 1988, Fowler noticed, a number of chemists noticed that these carbon molecules were forming roughly spherical shaped molecules. The first was fullerene, I believe, which is 60 carbons, but they found other ones too. So in the Fowler article, they discussed what I'm calling our generalized Goldberg polyhedra.
By the way, he said fullerene, not fluorine, in case anybody misunderstood. Buckminster fullerene, buckyballs.
And instead of constructing the Goldberg, doing the Goldberg construction on a regular icosahedron, you can pick one of the icosahedral symmetries, and by maintaining just that symmetry and distorting the rest of it, you can get a lot of different configurations than just the one here. The requirements are that, of course, adjacent edges must be the same length. The other is that this line on both of the adjacent faces, triangles, needs to cut at the same modulo angle, modulo pi-thirds or 60 degrees. So that is the same angle modulo 60 degrees as that. But you can do scaling triangles, and as long as you meet those two conditions, and the third condition being 300 degrees around a vertex, you can do the same construction, a similar construction on something like this. This is an icosahedron that has been distorted but still preserves tetrahedral symmetry. You want to pass that around?
By the way, as far as I know, nobody else has done this work.
Well, that's from the Fowler article.
Oh, this is? Oh,
yeah.
No, I'm not a deep student of this. I thought this was entirely...
And this is the generation of a Goldberg, a standard Goldberg. So that's fully regular.
You notice that each of the vertices of this icosahedron lies at the center, in this case, of a regular pentagon, and all the other faces are regular hexagons.
And Fowler was primarily interested in the tetrahedral, but he also gave a derivation of, this is D5, so it's five-fold symmetry around this long axis. So it's like you take the regular icosahedron and stretch it or shrink it a little bit. And this ends up being pretty good for a case for the isoparametric problem. A lot of them end up being that. And then this one, it goes through, the axis goes through the faces, so this is kind of squished. And this has D3 symmetry, so it's got threefold symmetry.
These are prismatic objects, these last two.
Could you spell some of the names? We have some students here. So one thing would be Fullerene, I have you spell it. Fullerene and other names.
Could you repeat that, please?
I know, but we have students here, so we could spell the names. I mean, who could please write them down on the blackboard?
Write them down? Which names? Fowler or?
Which one do you guys want?
All of them.
Is it with two L's?
Yeah.
Uh-huh.
And that's after Buckminster Fuller.
Although the two people who won the Nobel Prize for the discovery of these objects as physical objects said 10 years later that if only they had known that Coxeter was there first, they would not have named them Buckminster Fullerene. They didn't realize that Buckminster Fullerene was 25 years after Coxeter, but he was a self-promoter and Coxeter was not.
Right.
So they deeply regretted that the name has come to be Fullerene. So I have to add that because Fuller was a hero here at SIU.
But Coxeter visited SIU, right?
Pardon me?
Coxeter visited SIU, I think, more than once. Coxeter?
Yes, because of my intervention, Coxeter and Fuller became friends after having regarded each other as enemies. And out of humility and modesty and generosity, to make up for his former animosity to Fuller, Coxeter came to Carbondale as Fuller's guest. They fell in love with each other. He stayed there 6 weeks and he wrote a book, a mathematics book, during the 6 weeks he was here called 7 Geometrical Essays. A little side note, a very curious side note.
So,
But I was the instrument of their kissing and making up. It's a long story.
so one thing I didn't bring a model for is I worked out a way to generate C3 symmetry. D3 symmetry has twofold symmetry axes perpendicular to the threefold symmetry axis. C3 does not. It may have near planes, but it does not have the twofold rotational axes. I also worked out a way to. I don't have a model for twofold symmetry either for the D2 symmetry, which has three axes, as in XYZ axes of rotation. And then I figured maybe we can do one with no symmetry at all. And that worked out. Here's the...
This is your invention, isn't
Yeah,
it?
that's my invention, the symmetryless generalized Goldberg. By limiting edge lengths, I'm able to build a catalog of these generalized Goldbergs for a given n, and then try to stabilize them, and that allows me to probe a given area. Unfortunately, find polyhedra which may be near optimal in for that n.
Oh, I see.
It also allows me to compare the results to Goldberg polyhedra, such as I was able to find, I think it was 10,1 that I looked at, that I found multiple generalized Goldbergs that were better than the Goldberg 10,1. Yeah. Which was one thing that I was kind of expecting to find, because even then I had thought that there was likely to be an ideal ratio for R and S over R.
This is the holy grail you were pursuing, isn't it?
Yeah, of course I haven't proved anything. Proof's going to require quite some work. I don't expect to ever be able to do that, but at least I can give numerical results.
Maybe when it doesn't have a symmetry, and then how can you see that actually? Can you prove there is no symmetry, maybe, or you have some technique to prove there is no symmetry?
Could you speak a little louder, please?
Oh yes. I was asking, the last. What about the last stuff that doesn't have the symmetry you told?
That's right.
But there's just some technique to prove there's no symmetry, or
Well,
you just use computer some.
It's called C1 symmetry, but what do you say to that? Thank you.
I mean, it's going to depend on how you define symmetry, right?
Yeah.
If you define symmetry to be, say, a homotopy equivalent, I'm pretty sure that there's going to be plenty of symmetry. It depends on your category what counts as symmetry.
C1 is the trivial symmetry, it's the identity.
Yeah.
Except I
Every
don't.
object has C1 symmetry.
So maybe you can define the map from the depth to the sort of the automobile map from depth of the itself, and then except the identity map, there is no such a function. And then, or something like that. I'm just asking, that you have some techniques or some observation that proves there is no symmetry.
Well,
I think you could do it by some kind of exhaustive thing, because you have to have a look at all the mappings. There's only a finite number of things, so you try and map one face to another face, and then you have to tally up the faces around it, and then to show that it can never be done.
well, starting out with your generating polyhedron, that has no symmetry based on basically what you said. And that determines where the pentagons are. And if the vertices have no symmetry, then that's going to force the result to have no symmetry because of the pentagon positions. So you solve it for your generating polyhedron, where you only have 20 faces. The other way, I can take the result and look at the result faces, the hexagons and pentagons, and I can categorize them. I can say that these are identical or mirror image of these. That's how I get to tell, that's how I tell the symmetry of the final polyhedron, is by examining the pattern of face geometries and seeing which ones are the same as which other ones. Yes?
Can we use the tensor of moment of inertia to show if it is?
Could you speak up, please?
Can we actually use the moment of inertia of the polyhedron to show if it is symmetric or not? Because it's in 3D we have a tensor, and if it is symmetric, then we have we have symmetry about the different axes of
You could in principle, but it's more work to do it that way. Wayne's way of, I also used earlier, seeing if a face of given area has replicas among the remaining faces that also have that area, and if so, how many replicas there are. That's the fastest, computationally fastest way of doing this. Parenthetically, Wayne is an expert at big O. Most of you know what big O notation is. Wayne actually speeded up the structure of a program that my master's student, Dave Overton, wrote for this problem in 4 dimensions. He converted it from big O of 4 to big O of 3 in a matter of a day or two, which is no mean accomplishment. So computationally efficient, Wayne is a very experienced software engineer and programmer, and we look for the computationally most efficient ways of gaining information about these polyhedra. Is that a fair statement? Wayne?
Yeah, but
It's not the
yeah,
whole story.
basically I took Overton's and reduced it back to 3D and made use of that. So I was really improving on my stuff, not Overton's.
Well, use the ideas from this four-dimensional
Yeah,
to
yeah.
improve your three-dimensional program.
Yeah, I improved that by probably close to 1, more or less. I reduced the exponent by somewhere around 1.
That's so.
Yeah.
What language are you using?
Dave
Just-
Overton's
just
thesis is
see.
in Morse Library, by the way. If anybody is crazy enough to get interested in this problem in R4. When I returned his thesis, which was signed out, so you'll find it in Morse Library.
So,
I didn't get your point. How you want to evaluate symmetry using point of inertia? Because
Okay.
when you take this, you lose details of the shape.
I mean, if I have this shape, I can set some arbitrary coordinate and calculate the moment of inertia about that coordinate. So I get a tensor, and if I can find this kind of eigenvalue tensor for this one, which is diagonal,
So you
so
rotate,
it
in
has
fact, the
some, there is
coordinates.
some coordinate which is
Yes.
symmetric for this shape.
So you change the coordinate system for different coordinate systems.
Yes.
You compute it and ours.
Yes, I can back
It's an interesting idea. It
Yes.
just suggests that it's not the computationally most efficient way to sniff out the symmetry of a polyhedron. It's simple, but I could be wrong, but I think that the areas of the faces. It's an easier way to do it. It's just slightly, at least slight improvement. Slightly advantageous, but I could be mistaken.
so
It certainly worked, your idea is interesting, don't you think? The moment of inertia.
so continuing where I was, other things that I have found by probing these, by looking at these Goldberg pairs, is that as you get to larger n, the pentagons seem to shrink more than I had imagined. Looking at the ratio of the pentagons area to the average hexagons area, given that if they have the same edge length, they'll have about a 0.66 ratio. The pentagon will have an area that's about 0.66 of the hexagon. What I found is that you start out at about 0.8 or 0.9 for about 32-sided Goldberg. And by the time you get to 6,000, it's down to about 0.55. And it seems to decrease in a fairly regular manner. The other thing is that in looking at the Goldberg pairs, the Goldberg polyhedron with the lower S to R ratio seems to have more variability in sizes of its hexagons than the one that's 1-to-1 ratio. And really,
Remind people again what a Goldberg pair is, they made it for
that's two Goldberg polyhedra with the same number of faces, but
completely
distinct.
different R and S values.
Yeah. Now you can swap the R and the S, and the only thing that will change is the handedness of the Goldberg polyhedron, and that's why I had R being greater than 0 and S being less than or equal to R and greater than or equal to 0, just to constrain that. So even if, so you have Goldberg pairs that are really distinct polyhedra, but have the same number of faces.
It strikes me as nothing less than magical that two polyhedra that have the same, that Goldberg proved that for any Goldberg polyhedron with n faces, there is another quite different pair of R and S values that generates a polyhedron with the same number of faces. And that's a quite non-trivial result, as he himself was aware of and emphasized in his paper in 1937 when he discovered it.
And they both approximate the volume with the same.
Yes, but it turns out that one's always better than the other.
Okay.
Far better. That's what I'm getting at. That when R and S are approximately 1-to-1, it seems to be better than when one is significantly larger than the other. I think that's about it for now. Are there any questions? Or?
How about when R is equal to S itself, when they're both equal? How about when they're both equal, R equals S?
Yeah, then that's a 1-to-1. And that I'm guessing is the best situation. But I don't have any proof of that. When you're up at 6 million faces, the best pair you can find has about 0.87 ratio. You with 1-to-1 and 0.87 to 1 is a pair. And in that case, the 1-to-1 beats out the 0.87 by, but it's in like the 10th decimal place that you notice that.
Could you show your slide of a beautiful golden colored image of?
Well, it's not on the computer. I can. It's on. You still have the.
Yes.
It's in. Where is it? Say talk. And go to the last slide.
So.
Yeah. It doesn't show up very well. That's 1012. Or let's see, 1112. That's me. Alpha North sister.
Okay, what are we doing here? Let's stop that.
Not in slideshow. Just
No.
There you go. This was a more general slideshow for earlier this week.
Does it Goldberg polyhedron?
That is, I don't know. I don't remember now.
I thought you said
That might be just a D5. That might be the best. But by looking at it, you wouldn't know the difference. You'd have to very carefully look for pentagons and see if yeah. So.
The golf balls, do they use any of those Goldberg polyhedra?
Wayne's talking about the icosahedron a lot, and some virologists claim that the 7 most common viruses, including the common cold virus, have perfect icosahedral symmetry. In case anybody's looking for justification to study this wild and woolly problem, that's one of them. And then the slight connection to the fullerenes is another. And the study of nanoparticles is another. There's the Ulam conjecture, which is that the sphere is the worst convex shape in existence for a packing density. That if you chamfer, to use Goldberg's favorite word, truncated, if you take a little slice off a sphere and move a little starting to tap, and you will be able to pack a gazillion replicas of that modified shape with a slightly higher packing density than you can for the sphere itself. And Stanisław Ulam, not Ulam, right?
Yeah, Ulam.
Stanisław Ulam conjectured, among many things, that the sphere is worse than any other convex shape of packing. And there's a very active research group at the University of Michigan in Ann Arbor of 6 or 7 people headed by a lady whose name I've forgotten, and a German physicist there named Engel, Michael Engel, was very interested in nanoparticles, and he's interested in the question of whether these isoparametrically optimal stabilized stationary states, whether they have any interesting packing density optimality properties. Well, you didn't mention.
Number 8 there?
The reason I got interested in this problem in the early 1980s, I had a casual interest in it even before then. But Victor Klee, about whom a fascinating mathematical biography, not so much personal biography, has been posted on the web by Joseph Malkovich, a geometer at York College, York University in Long Island, New York. Joseph Malkovich posted, and it's on, I have a link to that on my own website. He posted a mathematical biography of Victor Klee, who was the man in the 20th century who did more, along with Michael Goldberg, to promote interest in this problem. He spent his career at the University of Washington, Seattle, where he and Franco Grünbaum formed a team of the 2 strongest geometers, classical geometers in the United States, I suppose you could say. Victor Klee proved in 1986 that the Lindelof condition of centroidal tangency to an inscribed sphere or hypersphere is true in Euclidean spaces of all dimensions. But Victor Klee he made one blunder in his life, a very tiny blunder, but I'm a nitpicker, and it's not very often that in fact, never on any other occasion that I ever detect a blunder by an eminent mathematician. Victor Klee published, in the American MAA, Mathematical Association of America, published 2 videos about geometry, one two-dimensional geometry, one three-dimensional geometry, with accompanying booklets that amplify his discussion in the videos very considerably. And in there he made a rash and, as I found, erroneous conjecture. All of you are too young to remember the introduction of the HP35 to the world. It happened in 1985, roughly. There was exactly one for sale in Carbondale. It cost $395. It had reverse Polish logic, and TI was the only other manufacturer of pocket calculators in those days in the world, as far as I know. And so I heard about this somehow in some local store, and I bought the only one in Carbondale. I was the first owner of the HP35, and I just discovered Victor Klee's suspicious-looking conjecture, which is that the optimal convex polyhedron, in the sense of the isoparametric quotient, that is to say, the polyhedron that does the best, the polyhedron of n faces, this is n is equal to 8 here, the best n equals 8 faced polyhedron, in the sense of snuggling down to an inscribed sphere with the smallest possible volume and the smallest possible surface area. No, everything here that sticks out of the inscribed sphere, you're to imagine, is extraneous, so that's waste. The minimum waste the polyhedron with the highest IQ, the roundest polyhedron, has the following property. Suppose you're in the plane, just think of this in 2 dimensions. The fattest triangle that you can describe in a circle is the equilateral triangle. And similarly, the fattest quadrangle is the square. Well, the smallest triangle you can circumscribe about that same circle is also an equilateral triangle. And we know that this is called the polar of this one. The midpoints of the edges are the points of tangency for the exterior triangle. They coincide with the vertices of the inscribed triangle. Victor Klee rashly, maybe it's the only rationing he ever did in his mathematical life, I have no idea, but he rashly conjectured that this is true for all, this is true in R3 as well as in R2. It's true in 3 dimensions as well as the 2 dimensions for every value of n. And it's certainly true enough for the cube and the regular octahedron homotopy. The vertices of the regular octahedron inscribed in the sphere certainly do coincide with the centroids of the square faces of the circumscribing cube, and so on. True for the prism, and true for the tetrahedron. But when you get to n equals 8, it smelled like rotten fish to me. So I went out and I bought the HP 35, the only one in town, and I found that he was off by a few quarts in 1,000. Or maybe it was a few quarts in 10,000, I don't remember. So then I got interested in this problem. One thing led to another, and then with mainframes being at least 1,000 times slower than pocket calculators are today.
Alan, can you write the name of the web page where you have all your geometric stuff? How do you
Possibly another time would be better, because I do promise folks a chance to get out of here on time, because I know people do have other obligations.
Just 1 letter more.
Thank you very much for the talk.
Grammatically bad German, that's the name of my website.
Sean John.
So I understand there are refreshments upstairs, so I hope many